We're all really excited for all the interesting speakers and authors that we have scheduled to talk today, and really excited and looking forward to all the discussions about virtual reality, augmented reality, mixed reality, and robotics. So first off, we just really want to thank all the authors for submitting their works here. The submissions this year are really interesting and innovative, and I'm excited for everyone to see the talks. And it was also really inspiring to see how researchers were able to come over and handle the difficulties of doing HRI research during the COVID pandemic. And so also we really want to thank all of our two keynote speakers, Casey and Paromita, for joining us here today. They're going to present on some really interesting and important topics spanning from ethics and tech to space applications. So I'm pretty excited about that. Just before we begin, we're just going to cover some basic logistic information. So we'll be running all the talks and discussions here on Zoom. And we have some scheduled opportunities, which you can check on the program web, our program page on our website. But we'll have some opportunities for everyone to network with some other attendees. And really, we really encourage everyone to be able to engage here live and talk together. And so we'll actually be having some time after all the lightning talks to go into some breakout rooms. And one thing we noticed based on all the submissions was that there were three broad themes among the papers. One was mixed reality for human-robot interaction. Secondly was about virtual reality for human-robot interaction. And a third grouping focused on virtual reality for teleoperation and telepresence. So what we've actually done is we've grouped all of the paper submissions into one of these three categories. And so you can find this information under the breakout session information on the program page. And what we'll do is we really encourage authors in that same group during the breakout sessions to talk to each other and see what kind of similarities are between your works. And we encourage all the other attendees to join in and talk with the authors. So besides the live Zoom meeting that we're having here, we also have a Slack channel, and we'll be dropping that link in the Zoom here if you don't have access to it. And so everyone should just go there and join it, since we'll be assigning every paper a channel. And what you can do there is go in and ask any more specific questions you have for the authors, and try to maybe even have longer discussions maybe over chat. And also at the end of the two keynote talks, we'll have some time for questions. And so we have a moderator for each of the talks. And what you can do is we'll be accepting questions from the audience. And so you can either use the raise hand feature on your Zoom and we'll call on you so that you can unmute your mic, or you can type your question in the chat and then we'll just read it out for you. So you can use either one. And also we'd really like to make sure that we respect everyone's time, since this is a virtual event. We're all maybe potentially over the world. So we'll be trying to follow the schedule timing as best as possible. So speakers should just make sure to keep their talks within their time slots, or otherwise we might just have to end you off a little early. But don't worry, there's plenty of times for discussion and questions, and those can happen during the breakout sessions or over Zoom and Slack as well. So also, for those interested, all of the accepted papers and PDFs are currently uploaded on the website program page. So you can access them all there and check them out so that you can really make sure to ask more pointed questions during when you talk to the authors. And we really want to give all the authors opportunity to speak with attendees and get some good feedback and integrate it into your work. So we'll be accepting the final camera ready versions of the workshop papers over the next 2 weeks, so that you guys have time to integrate it into your final submissions, which will then be uploaded for everyone to access. And also for everyone that's in the Zoom chat right now, you should have the ability to change your displayed name. If you go to participants and you can click on yourself and rename yourself. And so we encourage everyone to include any information they'd like to share about themselves, like either their pronouns or their affiliations. And also, if you have a Twitter, we'll be tweeting under the hashtag VAM-HRI. So please feel free to use that hashtag. And if you want to see what's going on or post anything with the conference, please, we encourage you to use it and follow what's going on with us on social media. So that's about it. So if you have any questions, please feel free to reach out to anyone in the chat who has the organizer tag on them. But otherwise, thank you so much for coming. And I'm really excited for all the talks and discussions and to meet everyone here today. So that's it. So I think we can just jump into it. So I'll hand it off to Christine, who's going to introduce our first keynote speaker. Thank you.
Thanks, Eric. It looks like Dr. Fiesler is here. So I will start that introduction. Hi. So thank you all for coming today. I'm Christine. I'm a PhD student at the University of Colorado Boulder. And I'm welcoming our first keynote speaker, Dr. Casey Fiesler. When the organizers were brainstorming speakers to invite, we knew we wanted someone who could speak on issues of ethics in technology, hopefully guiding us to make ethical decisions in our work in augmented, virtual, and mixed reality in HRI. And when the possibility of inviting Dr. Fiesler was mentioned, there was tangible excitement and anticipation. Dr. Fiesler is an assistant professor and founding faculty in the Department of Information Science at the University of Colorado Boulder, where she researches and teaches in the areas of technology ethics and policy, as well as social computing. And broadening participation. Her work on research ethics for data science, ethics education and computing, and broadening participation in computing is supported by the National Science Foundation, as well as Mozilla and Augmented Network as part of the Responsible Computer Science Challenge. She holds a PhD from Georgia Tech in human-centered computing and a JD from Vanderbilt University Law School. Please join me in welcoming Dr. Casey Fiesler.
Hello, thank you. I'm happy to be joining you from my living room. I know I do that awkward thing where I'm like, and now I'm going to share my screen. Let's see. All right, so full disclosure, I know very little about AR and VR, and perhaps and not much more about HRI. So I'm going to talk about some kinds of general ways to approach issues of thinking about ethics in technology. And I'm going to start with this slide, which is where I learned everything that I know about AR and VR from when I was making my slides this weekend. Except I'm a big fan of Pokemon Go, and so I'm very interested in what the code of ethics might be. I sometimes joke that given my research, it's just making slides like this over and over and over until I retire. But the point of this is, for most any segment of technology, subfield of computer science, etc., there are some kinds of ethical issues that come up. I spend a lot of time thinking in particular about like AI and data science, and those get it a lot heavier. Like, I don't know where, the ethical controversies are for like operating systems in theory, but I'm sure they're there somewhere. But certainly the space that you all are thinking about today is one in which people are having conversations like this, judging from a 10-minute Google News search that I did a couple of days ago. And I want to show you one of my other slides like this that I've made, and it's about one of my personal favorite examples, which is Zoom bombing. The reason that I use Zoom bombing in particular as an example is because when, we were faced with the current dilemma as the world as it is, and everyone moved on to Zoom, et cetera, and then like this new awful thing started happening, brand new way to harass people, new way for like people to be terrible. And everyone's writing about all these awful people and how come this is happening, et cetera, and like why is this possible on Zoom? And Zoom CEO said in an interview that they had never thought about this. Like, it never occurred to us that someone might use our technology in this really awful way. And I have a lot of thoughts about this. I'm not going to be talking a lot specifically today about like issues of diversity in the tech force, but I will say that is one thing that comes to mind here. I have to say that I mean, obviously hindsight is 2020 and it's difficult to know, but I feel like if someone had described Zoom to me, like the privacy protocols and like, oh, it's, it's this 8-digit number and things are open. And I feel like if someone had described this to me and said, how might people misuse this technology? I probably would have immediately jumped to like, people are going to go into random Zoom meetings and show people their genitals. Like, I do not think that is outside the realm of possibility. However, I also think it's possible that the people who are most likely to come to those kinds of conclusions are people who have a lot of experience with harassment online, which, includes women and queer people and people of color. And I just named like groups underrepresented in computing. So I will just make that side point as we continue. And this idea of like, should we have thought about it? I think is actually a really important idea. And it brings to mind this quote from Isaac Asimov that although problems and catastrophes may be inevitable, solutions are not. And one of the reasons that I think solutions are not inevitable is because I don't think that people always recognize the catastrophes are inevitable. There's a quote of a tweet in the book Design Justice by Sasha Costanza Choke that is basically something along the lines of, if you create a new social media platform and you don't have, the ability to block users like from the start, like this might be a sign that white men designed your social media platform. And at this point, we know that online harassment happens, right? Like this is not new. This is not something that should involve this like great stretch of the imagination. So that's one example. We do think a lot about like, or not think a lot about, but like we know that there are going to be problems, right? So we think about technical debt a lot in the technology design process, like this idea that like, yeah, there's going to be some bugs, obviously. We're not perfect. Tech design isn't perfect. Coders aren't perfect. But, like, we got a release date. Like, let's push this thing out. And we know that we're going to have to fix some bugs. And it's probably going to be more annoying to fix them later than to fix them now. But at least we'll know what they are. And we don't have to figure it out ahead of time. And so technical debt is this, like, implied cost of those future bug fixes by not doing it now and waiting to see what they are. So I've been thinking about this concept of ethical debt. And my PhD advising Natalie Garrett and I wrote an op-ed about this for Wired that came out last year. And it's basically, again, this implied cost of not thinking about things now, except instead of like, oh no, this submit button on the form doesn't work. It's like, perhaps our technology will have some huge social cost. Maybe it will become become so embedded in the social fabric of society that it can influence the outcome of democratic elections. Or, maybe people will Zoom bomb. And part of the problem of ethical debt as opposed to technical debt is that the harm's already been done in this case, right? Like people who are Zoom bombed cannot unsee. And so how should we be thinking about these kinds of implications and harms now before it's too late? So I'm only going to talk about this next bit briefly, but I wanted to bring this up in case anyone wants to ask questions or talk about it more. But, I often think that part of this, basically the not recognizing how critical a part of the design process this is, comes from this sort of general idea that like, well, I'm just the engineer. There's ethicists whose jobs are to think about this. And like, I often hear, well, product teams should have philosophers on them. And like, I'm very like, more jobs for philosophers, yay. But also this should be everyone's job, right? And I actually think that part of the like impetus behind this particular philosophy comes in part because this is how we teach ethics to computer scientists a lot of the time. And this is a quote from an op-ed that came out around Cambridge Analytica that really resonated with me, which is this idea that software engineers treat safety and ethics as specialties rather than the foundation of all design. And I was like, oh, yes, true. This causes so many problems. And also, it makes total sense that this would be the case because we tend to teach ethics in computer science this way. You know, this varies a bit, and there have been certainly movements even in the past 3 years since I wrote this piece here, movements towards integrating ethics and social impact like into technical classes as opposed to siloed and standalone classes, or like outsource the ethics to the philosophy department or whatever. I think that this is really important. Like, ethics should not be something that is someone, you know, is a specialty. Like, I mean, it's a specialty too, right? Like, that's me. I want a job. But like on a construction site, there's someone whose job it is to be the safety engineer. But that doesn't mean that like the person putting up the drywall sees a live wire and is like, well, that's for the safety engineer to think about, and just walks by. Like, everyone needs to be thinking about this. So anyway, my pithy tagline here is that if you work in tech, you're not thinking about ethics, you're bad at your job. If I could wave a magic wand and change one thing about like attitudes in the tech industry, it would be this thing. And if you're interested in thinking about like how to teach tech ethics added into your classes, etc., I don't actually want to use the word curate because that suggests I do more work than I do. I made a publicly editable Google spreadsheet that now has almost 300 tech ethics syllabi on it. But then going back to this idea, so okay. Let's say that we are now interested in, you know, closing the gap for ethical debt and maybe teaching some of this to computer science students. How do we do this? And part of the argument that I often hear is like, well, how are we supposed to see the future? Like, I'm not clairvoyant. I don't know what bad people are going to do with technology. Though, you know, again, I feel like if you're creating a social media network and it doesn't occur to you that people need to be able to be blocked, then like, where have you been for the past 30 years? But that is a reasonable thing, right? So something that I have been thinking about a lot in my work recently, and this is why I'm suddenly quoting Asimov at you, is how do we think about speculation, and in particular ethical speculation, as part of the design process with technology? And so I'm going to share a little bit about a specific teaching exercise that I use, but I'm certainly thinking about this much more broadly than just in the classroom. So students are very interested in Black Mirror. And I know this because I teach an ethics class, and everything I talk about, someone's like, did you see the episode of Black Mirror? Or like every TikTok I've been making about tech ethics recently, someone's like, did you see that episode of Black Mirror? Or did you see that episode of, you know, whatever. So this is compelling, right? My theory about one reason why Black Mirror in particular is compelling is because it takes like current technology, like our current anxieties about technology, and pushes them just like a little bit further. Like, you can see the line between here and there. This isn't like Star Trek. It's like, oh yeah, that's, we're going there in 5 years or 10 years. One of my favorite examples is Nosedive, which draws on anxieties that we have around things like social credit scoring and the constant, you know, this anxiety to like feel like you're performing on social media and to be a perfect person, etc. And then, of course, hopefully an episode that most of you have seen, Playtest, which is about a virtual reality game. And actually a lot of the like news coverage and responses to this episode was like, yep, that's where virtual reality is heading. Isn't this terrifying? You know, and I think this idea that like we can get really invested in thinking about the ethical implications of some technology that someone might create in 20 years or 100 years or whatever. Like students in particular can get very excited in thinking about that. Like discussing this episode, very engaged. And if you can do that, if you can think about what the possible misuses of some technology someone might create in 50 years is going to be, there's no reason why you can't do that exact same thing with the technology that you're creating today. And you know, this idea of thinking about bad actors in particular is only one component of that, but it's an important one. You know, HCI researchers often use user personas to imagine like ideal uses of their system. Like, you know, we're building a social media platform and here's our like soccer mom user persona, and here's our like college student user persona. Well, I also want to see the abusive ex-partners stalking their ex user persona. I want to see the person who thinks it's funny to show strangers their genitals user persona. And then you design to make it more difficult for those things as opposed to making it easier. So for a teaching exercise, I've created this slide deck in Google Slides that has these templates so that students can actually create their own episodes and make something that looks cool like this, because like I was trained as a constructionist in learning sciences, and I think that making artifacts helps people learn. So if you want to try that out, please do. There's the URL. You can do it in your product design team if you do want, or like your research group. I sometimes in my research group will like have students, for example, write negative headlines for if their research was in the news, for thinking about how it might be perceived, for example. But then also on the topic of research, so this was a recent New Yorker article, who should stop unethical AI? And by the way, it turns out that the answer is HCI researchers, apparently, based in part on kind of what got discussed in this article. But this is largely about the discussions around ethics that are happening in the research community. So there were nods to, you know, NeurIPS and the ethics review and how that blew up. And there's mentions of the SIG-Chi Research Ethics Committee, which I've been on for quite a while, and the process that we use. Because, you know, one of the points here is that computer science is kind of behind in terms of thinking about research ethics. So I don't think this is true for like HCI researchers. People in computer science who are used to working with humans, this is not the case. The issue is more all that stuff that's not about working with humans, you know, which is not the case for what most of you here are thinking about, but this is it's kind of broader issue there. But the other thing is that it's not just about human subjects research. It's not just about like, oh, make sure you ask people for consent before you stick them with needles or whatever. It's also about thinking about the broader impacts of our work. And so this term that we tend to hear quite often these days is unintended consequences or negative consequences. How is your research going to change the world? And are you assuming that it's in a positive way? And this isn't to say that we should be rejecting papers. People always get very worried about that. This isn't to say that we should be clairvoyant and be able to think about everything. But I'm sure that, you know, if you thought hard enough, you can think about some paper where you're like, wow, I'm really surprised that there wasn't any discussion of the ethical implications of this work. And so researchers too, I think, should be doing this kind of speculation. So let me read this quote to you. My job is essentially to think up some difference in the world and make sure that the human reactions to it, the changes that society has built around it, feel right. To do my job well, I need to think through the unintended and unexpected consequences, the second and third and fourth order ripples. So this is a quote from Malka Older, who is a science fiction writer. And this is in a book called Media Law Through Science Fiction, which I highly recommend, in which she was interviewed. And I think this is interesting because this is the exact same thing that we should be doing. We should be thinking about how, if we are going to make a difference in the world, what are the human reactions to it going to be? What are the unintended consequences and the third and fourth order ripples? And actually, the first part of that Isaac Asimov quote is, "Science fiction writers foresee the inevitable, and though problems and catastrophes may be inevitable, solutions are not." So one of my calls to action is that researchers, technologists, and computer scientists should be thinking more like science fiction writers. And that is the provocation that I will leave you on. Thank you.
All right, thank you, Dr. Fiesler, for such a wonderful talk. All right, so at this point, I'd like to open up the floor to all of our attendees to ask questions. And how we would like to do this is either use the raise your hand feature on Zoom, or you can ask a question in the Slack message panel or within Slack itself, or is the Zoom messages or Slack. So yeah, okay, so any questions? All right, Taran, I see you first. Go ahead.
Hello, thanks for your talk. I'm curious how people are receptive to these kind of ideas about tech ethics, and if their reaction varies between academia and industry.
I've certainly got a lot of highly varied reaction to these kinds of ideas. Sometimes I get kind of complacent, and I'm like, how could anyone not care about this stuff? And think that it's like total. And then thankfully something will blow up, and I'm thinking of in particular like Pedro Domingos losing his mind on Twitter about NeurIP's ethics review, and that whole thing was like, oh, that is correct. Not everyone agrees with me that this is important. I would say that there's definitely some variance among different kinds of research communities. I mean, like I said, HCI people have been thinking about this stuff for a long time. But a lot of people who think, a lot of research communities where they're mostly working with data instead of people, which, means things like machine learning and data science. If you've never thought of your work as involving people at all, it's kind of reasonable that you might not have been thinking a lot about ethics, right? So there's definitely some variance there. And industry, the people that I'm talking to in industry care a lot about this, right? Like I've given, talks at Facebook and Mozilla and Google, and the people who invite me to do this are the people who care a lot. And then I'm sure there are lots of people who don't care as much, who don't talk to me as much. But I get, but the thing that I'll add to this answer that I think is promising is that attitudes, I think, are shifting a lot. Like the conversations that we're having today are a lot different than conversations we were having 5 years ago. And I think it's a really positive trend.
Okay. Next question we have is Carl Mueller.
Hey, that was great. My question, I guess, I mentioned something in the chat, but you sort of addressed that, that most of us kind of, I guess, naturally think of the good that our research will do. But I guess maybe on a related topic, in my own research, I like to think that I focus on the potential ethical concerns of my research. But sometimes the stuff that I sort of come up with isn't really actionable. So for example, my research focuses on learning from demonstration. So, making robots more accessible generally to maybe non-robotics experts. And sort of the ethical considerations, I think I was like, well, who can afford these robots? Who am I actually making this more accessible to? And in the weeds of working on algorithms and codes, what could I actually do to take action on those considerations when it just seems so distant to my actual research?
I think that's a really interesting, I think it's a really important question. And I'll also add to this a little bit of what you said in chat as well. Honestly, it is, I mean, a big part of this, I think, is even thinking about it at all. Like, so many people aren't even getting that far, right? And interestingly, I mentioned I'm on the research ethics committee for SIGCHI. I like the most, and one of the things we do is like if ethical issues come up during the review process, we are asked for an opinion, not like information, opinion, not decisions, et cetera. It all goes back to the program committee. But the most common outcome of that is that we ask people to add information to their paper. It's either because there's some details missing about ethical decision making, or it's because it needs some reflection. And the kind of thing that you bring up here, I actually think is a great example of something that, as a researcher, I don't think you should be expected to solve that problem. However, it's certainly something worth noting and kind of reflecting on what that means. And similarly, this question here about should ethics always focus on negative outcomes, and what about the good that technology does? I mean, I think I hesitate to say that this is what ethics is, because I find that technologists often like jump very strongly to utilitarianism because it's very appealing to turn ethics into math. However, there is a such thing as a cost-benefit analysis, and I think that talking about the potential good of technology in addition to the potential harm is an important part of that conversation. And so I'm working on this project right now where we did a review of basically every paper that has used Reddit data. And one of the things that struck me about it is how many papers are just like, we built a classifier for X, where there are then obvious ethical implications, like we built a classifier for domestic violence or something like this. That's a real example. And there's nothing in the paper about how this will be used, why it's helpful, why this is beneficial to society. And I think that if there are potential harms, then you should also be talking about potential goods. And then let's see, so the final part of that question then is sort of like the technical limitations. I mean, I think that can be valid, again, with this kind of cost-benefit analysis. I don't think that like it's too hard is like always a satisfying answer. But sometimes there aren't solutions yet for mitigating every kind of harm, but I would like people to at least be thinking about it, which is a good start, at least.
Okay. Next question we have is Abhijat, if you'd like to go.
Yeah, thanks. Thanks for the talk. My question, I think you touched on it a little bit before, was going to be about the role of peer review in sort of what you think the role of peer review is in sort of like setting the ethical standard for a field. Because I don't think we're at the point where we can agree as a field on like what ethical regulation should look like. Sort of, civil engineers have figured this out many years ago, but we're still getting there. So in this current state, what do you think the role of peer review is in that? Yeah, so I mean, so actually this is something that I've been thinking a lot about for the past 5 years or so, since I don't know how many of you are kind of part, HRI is not part of SIGCHI, is it? I forget. Or, okay. So the Research Ethics Committee for SIGCHI, which then handles like Chi plus all of the other SIGCHI conferences. Okay, so apparently also HRI is under our umbrella. Thank you, Tom. The reason that this committee was founded was in part because ethics was
starting to come up in review, like in the review process, in very inconsistent ways. You know, and people were telling me stories like, well, my paper just got rejected for violating terms of service, but like this paper over here did not get rejected for that. And so there was, and also reviewers were talking about how they weren't comfortable, like weighing, like I'm an expert on this topic, I'm not an expert on ethics. And so the committee was founded to help with that. And basically the idea was that it was people who, in part, it's people who do have some expertise on ethics to provide an opinion. So in a way, it's sort of like bringing in an R3 or an R4 to a paper to provide input on that particular thing. But the other charge of the committee was like, can we help the community move towards norms? Because there was definitely an understanding that there weren't any. And so the other thing the committee does is like hold town halls at conferences where like we discuss the most common issues that have come up, and people bring things up, and sometimes they yell at us. And I think that, you know, I think that that's very helpful, because it can be hard to form norms around these kinds of things. And I mean, something that comes up every time is like also like ethical relativism in terms of like discipline and geographical location, etc. But again, I feel like going back to that, like people need to be writing about this in their papers. Like that's one way that we form norms. Like I feel like people are really hesitant to do that because it's like, I can't bring up the potential like, what if no one would have noticed? I don't want to draw attention to what the ethical problems with my work is. And often people are making decisions about like why they did something a certain way ethically or why it's okay. And you might not want to write about it because like, what if someone disagrees with me? But that's how we form norms, is also by having good examples of things. So I do think that ethics should be part of peer review, in that I think that, you know, like for example, a method that is unethical is a method that is bad. I mean, it's not some sort of like moral high ground thing. It's that science is not like absent of, you know, consequences, etc. Like if you did a study where the method hurt people, I would argue that is bad science. I think that science has that responsibility, and that work probably should not be published. That said, it's almost never that cut and dry, right? Like, I mean, I actually can't off the top of my head think of a single time that the ethics committee suggested that something just be outright rejected. Like, and I don't know, maybe in some communities there would be more of that. But I think that, like, you know, I also think that people should be writing about ethical considerations in their methods sections, and not like as some weird, like I often see sort of like a section at the end of the paper that's like limitations and ethical considerations, and I'm like, what's your ethical considerations really a limitation? So I guess that's my answer, is that it is part of peer review, but I also think that it's important to be, you know, to have some people involved who are familiar with the ethical norms of the community and know how to evaluate that kind of thing.
Okay. Next question we have is from Robert Hobbs.
Good afternoon. I would appreciate your thoughts on the applicability of treating ethical concerns out in production worlds, much like we would any other risk that the organization is exposed to. For example, as an ethical concern of the demographics and some face recognition on par with the cybersecurity. The intent is to try and get, or the potential intent is to get the visibility of ethical risks on par with the other types of risk, so that it can be communicated clearly and consistently with those to the management, to the financial backers, to the auditors who come in, so we can justify any corrections that need to be done.
That's a great question, and I actually think that we have a lot to learn from cybersecurity in this sense. I mean, some of what I just described could basically be considered threat modeling. And I'm actually working on some research right now about this kind of speculation stuff that's drawing some lessons from cybersecurity. So my simple answer is yes, I think that's a good idea. And the other thing is I'll kind of add something to this context, which is, a lot of times something that will come up in these conversations is like, well, okay, Casey, like, of course we want everyone to care, et cetera, but like, some of these things you might be suggesting would really hurt Facebook's bottom line or Zoom's bottom line or whatever. Like, what if doing the ethical thing is directly contradictory to the business interests of a tech company? And I actually think that is one of the biggest challenges in this space. Though I will say, I also think that there are economic incentives for some of this, and that there's starting to be more. So, for example, I remember hearing somewhere that like someone did a study like that people were starting to use Lyft over Uber because of the perception of Uber as an unethical company. And there was so much bad PR for like the business practices and the labor practices of Uber that people were starting to use Lyft instead. And I do think that is legitimate. The other thing is I've heard about companies losing talent, that college students graduating and going to get tech jobs were less likely to go work at companies that they considered unethical. And I do think that both of those things, like bad PR and losing talent, like I would love to think that everyone cares just for the sake of caring. But if what I can get is like, we don't want bad PR, like I'll take it. But I absolutely think that these things are starting to be discussions in the context of like the business interests of the company. Some collaborators of mine who work at Data and Society wrote a report a couple of years ago. I think if you Googled ethics owners, you would find it. And they basically interviewed a bunch of people whose job it is at companies to be the ethics person and sort of what that means and the challenges that they face. Ethics owners. And I thought that was really interesting. I also think there's more and more jobs like that that we're going to see.
I was just looking at the EU's guide for trustworthy AI, and as you run through that 5 pages of listings of qualities, the majority of them apply to cyber or customer service or other type of risk factors. So it really can tie together very well, I would think.
I think so too.
Thank you.
Okay. Next question we have is from Dan Grohlman.
I have so many questions now, actually, but I will pick one, and I hope to have more discussions on this topic later. So you've talked about a bunch of different sort of solutions to the ethical problems, societal, regulational, or technical. And I'm wondering where you think the most promising effort is. Like, should we really focus on getting companies to build ethical technologies or build the technology ethically, or should we push more on government regulation or trying to force societal change? Like, if no one wanted to Zoom bomb, then it wouldn't be a problem.
Oh, that's such a good and hard question. I was just teaching like 2 hours ago, and we're doing regulation this week, and I was talking to students about Lessig's models of regulation, and it's like law and norms, and then like, what do you think's best? And that's a very hard question to answer. Despite being a lawyer, I do not tend to jump to regulation as the immediate answer to these things. In part, I guess my specialty is actually copyright, and I guess I've just gotten disillusioned that copyright law will ever change. On the other hand, I think a positive example of how regulation can have a big impact is GDPR. So I do actually, so I don't tend to jump to regulation as a solution, but when it works, I think it's great. And I do think that there are some cases in which we might need it. And I think that data privacy was definitely one of those examples. And I think perhaps facial recognition might fall into that category too. That said, the law is also very slow to catch up to technology. So like it's not like facial recognition is new and we're just starting to get to like where we're starting to get some regulation. Or like I just saw a new story the other day about a proposed law that will help with like deep fake revenge porn, which is such a just like mind-blowingly awful problem. And we've been talking for 10 years about how there's not good laws for like online harassment and revenge porn and these kinds of things. And we're just now getting to this. So, that's one of the reasons why I think that it's really important that we're seeing real, responsibility happening in the tech industry, because if you're creating a new technology, whatever the next, I don't know, amazing VR, AR thing, like actually I just, whatever Microsoft Mesh is, I don't completely understand what it is after having seen it, but like this is new, right? So there's probably not going to be any relevant regulations, and even if it starts to be a problem, the law is very reactive. Like that's the like the ultimate example of like ethical debt is like the law is not going to care about it at all until it already knows it's a problem. So that's one of the reasons why I think that responsibility in the tech industry is so important. That said, like I was recently doing a panel and someone asked me what the solution was to cyberbullying. Like this wasn't technologists, it was like a local like women's business meeting thing, and there were a lot of parents and they're like, what do we do about cyberbullying? Like, how do we teach kids this? And I was like, God, what a big problem. But that question actually made me realize like what I actually think is the biggest problem with a lot of this stuff. And I don't know what the solution, I'm going to identify a problem for you and give you no solutions, which is empathy. If ethics is in part about harm, you have to care about harm to people other than you. And so here's an example. My former PhD advisor wrote a paper a few years ago about Gamergate, where they actually interviewed a bunch of people who were like part of the Kotaku in Action subreddit. So like people who identified as part of Gamergate. And one of their findings was that they talked to people and they're like, so do you harass women online? And they would be like, no, we do not. And like, well, here's an example of like you sending a death threat to a woman on Twitter. And they're like, well, that's not harassment. It's just words. If someone sent me a death threat, it wouldn't bother me at all. Similarly, like I did a TikTok a few weeks ago about the paper where they were talking about AI bias and image completion, and like had a photograph of AOC in a bikini. I mean, a fake photograph, but they had a photograph of AOC in a bikini in their paper, and they took it out. But like I was talking about this, and someone was like, I don't understand why that's upsetting. If someone put a photograph of me in a bikini in a paper, I wouldn't care at all. And it was, someone clearly male identifying. And I was like, you might want to think for a second about how this might impact someone differently, than you. And so I do actually think that's a huge problem, and it probably is at the root of a lot of types of trolling and other kinds of bad actors. And I don't know I have absolutely no idea what the solution is. So I guess my answer to your question is we probably can't rely on regulation. And which is why I'm really pushing towards tech industry change, because the other problems are so much harder that I don't personally know what to do with them, even though they're arguably the most important.
Well, thank you. I would be thrilled to talk more about this with you later, but I see the rest of my time.
Thank you.
Okay. And with that, I think that's going to wrap up our Q&A session. I'd like to thank everyone for all the questions, and I'd like to give a special thanks to Dr. Fiesler for the wonderful talk and sparking all this great conversation. I'd like to point out that a channel has been made within our VAM-HRI Slack that's going to continue on this conversation. So feel free to move on over there and ask questions, talk amongst yourselves. And finally, it looks like we have a break coming up. So we'll have 10 minutes for those who want to chat in the Slack chat or in the Zoom channel. Go ahead, grab water, grab a snack, whatever, take a break. And then at the top of the hour, we're going to start our lightning talks. So I'll meet you back here then, and thanks for coming. All right, so I'm going to go ahead and get us started again. What's going to happen now is we're going to go through our first half of lightning talks. We're going to go through 5 papers, and we have 30 minutes to do it. So the way these talks are going to work are each author is going to have 5 minutes to talk. I'm going to be moderating this, so when your 5 minutes is up, I'm going to let you know that your time's up and give you 15 to 20 seconds to wrap up, and then we'll just move on. So let's get this started. First author is David Pulges. If you'd like to share your screen, go ahead and start.
Yep. So, hello everybody. My name is David Puljes, and I will be presenting our work together with Bowen, Ke, and Bjorn on hand-mounted AR intention recognition. So just a bit of a background how it all started. So it started with the project SafeLog, where we sought to bring humans inside automated warehouses. So we had a nice safety vest, AR glasses, and so on. But one of the main points was how could we estimate the goal of the human with onboard sensors? That's not only interesting to improve general human-machine interface, but it's also very important to detect if the human is in distress, and it also greatly increases efficiency in robot path planning. So the original work was done by Petkovic et al. In the human intention estimation based on the hidden Markov models. So here I was basically doing the AR and VR testing. So on the right in the video, you can see sort of a virtual representation of the small warehouse where we did our tests. Later on, we did also a large-scale test in VR, actually. So how it works, basically, we would build a Voronoi diagram in between points to find the shortest routes from node to node. We would define a hidden Markov model with X different goals, including an unknown state and an irrational worker state that would help detect if the human is in distress. And basically, we would use a Viterbi algorithm and a human and a validation vector to calculate human intention. And this has proven to be much better than just using motion, because we are also including possible states as well as the previous history of motion. So our work here basically then decided to extend the concept. So instead of a 2D HoloLens pose, now we have a 3D hand position and a gaze direction. So on the right, you can see a video and the estimation of different probabilities of the goal. The Voronoi diagram we simplified to Euclidean distance in 3D, which proved to be adequate, as the hand motion is generally not that constrained as a human motion inside a warehouse. And the motion validation vector was slightly changed to include gaze. So what can this be used for? So for example, here we can see different objects. You can see that the robot wants to go towards a green goal. But as it detected a human wants to reach the same goal, the robot stops and then goes back to the start position to select a new goal. So this is just a mock-up basically, but it illustrates the main intended purpose of the algorithm. The second purpose, here you can see it can also be used to order robot towards the target more intuitively. So basically just reaching for the cube would send the robot going towards the middle objective. So in this case, represented by a red cube. Then that's basically just the basic framework that we are basing our research on. So we want to extend it further. One great possibility is hand skeleton tracking. So we chose a paper-generated hands for real-time 3D hand tracking, published in 2018, which actually works very well with general skeleton tracking, as we can see here, and also object manipulation, which will be quite important to allow general action recognition. We're also working on the automatic generation of goals. So basically, if we have a table where the human and robot should cooperate, let's say there are objects on the table, so we would use a YOLO version 4 detector, as you can also see here on the right, to basically create bounding boxes. And then based on the ego motion of the HoloLens and the depth sensor, we could actually then create 3D bounding boxes of specific objects and then automatically basically generate the goals that previously we have to define. And finally, we have the robot intention visualization. So here we're also exploring different avenues. One is virtual execution. Again, as you can see here on the right, in this case, it was used to preview a program. But in our case, it can also be used if you have a program and the human is cooperating and the robot is dynamically changing its program. One can preview basically the motion of the robot before the robot executes the program itself. And the second, more light version, let's say, is just to display goals, basically as holograms. And to compensate for the low field of view of the HoloLens, we also intended to use 3D spatial sound.
Okay, that's
different
so
objects.
go ahead and wrap up.
Yep. Basically, that's it. So thank you for your attention. And if you have any questions, I'll be in the breakout session and the chat. Thank you.
Great, thank you. One thing I wanted to quickly mention is that you may have noticed, but in the Slack, you're going to see there's now a channel for each paper. So feel free to start discussions, comments, questions for the authors in those channels. And with that, I'm going to move on to our second paper, which is Catherine Mimna. If you'd like to share your screen, go ahead.
All righty. Can you hear me okay? Okay,
You're
so thanks. Hi, everyone. I'm Catherine Mimna, and I'm a doctoral student in the Perception Engineering Group at the University of Oulu in Finland. I'm here today to present you my paper defining preferred and natural robot motions in immersive telepresence from a first-person perspective. So I'm going to start by asking you a question. What is natural motion? What comes to mind when you think of how you move naturally or how other people move naturally? For me, this brings to mind the Ministry of Silly Walks from Monty Python. Perhaps it's the case that motion that's natural for you is not the same as natural motion for me. But what about robots? Is natural robot motion the same as human motion? Should it be? There's been plenty of research on this topic, but typically it's from a first-person perspective or from a third-person perspective, excuse me, of someone looking at a robot and judging whether it's moving naturally. But what about from a first-person perspective, when someone is inside of the robot looking out? What then is natural motion, and why should we care? Well, perhaps people on board mobile robots or immersed in a robot prefer for it to move naturally, or maybe they don't. This is the question that I tried to answer with my research. So let's talk about the tech that I used. The system was immersive robotic telepresence. So telepresence is the ability to be in a remote location via technology, kind of like how we're all virtually together in Colorado right now. And robotic then refers to a simulated or a real robot, and immersive refers to the fact that we're using a virtual reality head-mounted display. So you can put a 360 panoramic camera on a robot and it can live stream to a virtual reality headset, and that allows the person to look out from the robot from a first-person perspective. So what is this used for? Two specific examples. The Da Vinci surgical system allows doctors to control robotic arms to perform remote surgeries using an immersive display. Or this is an example of the Robonaut telepresence system developed by NASA for space exploration controlled through virtual reality. Other applications, such as for therapeutics and search and rescue, have been developed as well. But there can be some problems that come when you use this technology. With virtual reality, there can be something called VR sickness, where you might have headache, eye strain, or nausea. And when it comes to the mobile robot, they can be difficult to control manually. So there might be latency, or just like if you're controlling a remote-controlled toy car, they might be hard to maneuver. So that's where my research group comes in. These problems with VR sickness and with difficulty in manual control can be addressed by planning autonomous motions for the telepresence robot that take into account the experience of the person inside of the robot. We call this human perception optimized planning, and you can check out this paper by Israel Becerra in our group on how we implemented a multi-objective optimization framework and how that was able to reduce VR sickness symptoms for subjects in immersive telepresence. So the paper I'm presenting to you today discusses an evaluation of user experience when comparing paths that were generated with this perception optimized path planning when compared to a traditional path planning algorithm, the RRT. We ran a user study and simulation with 36 subjects. Participants watched pre-recorded videos of 3 paths in an Oculus Rift S, and they rated the preference, comfort, and naturalness of each of the 3 paths. The paths navigated through a virtual museum built with Unity. So back to that burning question about what is natural motion from a first-person perspective. Well, here you can see a graph of responses to an open-ended question on why a path was chosen as natural. The top comments regarded the turns and the distance to objects in the museum. We also frequently heard about the ability to see museum and to view the art. Another piece was that for every comment that subjects gave us about regarding naturalness, for example, naturalness is moving in a straight line, somebody else would give us the opposite answer, like naturalness is wandering around. So it seems when it comes to understanding natural motions from a first-person perspective, the answer is not straightforward, some pun intended. But fortunately for us, there is a lot more work to do. Speaking of which, our next study is going to rerun the same paths through an empty museum to see how naturalness is considered in a broader context. And we're also going to run studies with a mobile DDR robot on campus at our university. So the study looked at more than just naturalness. There was comfort and preference. So if you want to see the full paper, it's been submitted to IROS and it's now available on arXiv. So thank you so much for your attention, and I hope to get to talk to you during the Q&A.
All right, great talk. Thanks, Catherine. Next, we have Taran Mott. Go ahead.
Okay, can everybody hear okay?
Yeah, I can hear you.
Great. Okay, hello, my name is Taran Mott. I'm a PhD student in the Mitra lab at the Colorado School of Mines. And today I'm going to share our work on augmented reality for enhanced situation awareness in human-robot collaborative search. In the future, human-robot teams will need to complete time-dominant exploration tasks in unknown environments. These kinds of tasks occur in situations like disaster response, search and rescue, and firefighting. One of the most important considerations for human-robot teams in such tasks is the situation awareness of human teammates. And augmented reality is a compelling tool for human-robot communication in this case, because the right AR visualizations can help human teammates build and maintain situation awareness of their task context. Situation awareness is a concept with 3 levels. Level 1 is grounded in perception. It refers to someone's awareness of stimuli in their environment with respect to basic characteristics like color, location, and shape. And level 2 is grounded in comprehension. It refers to someone's understanding of the meaning of stimulus in the context of their task. And then level 3 is grounded in projection, and it has to do with whether someone can form reasonable predictions of near future states in the environment. So we used a simulated human-robot collaborative search task to investigate the effect of augmented reality visualizations on situation awareness. And our task environment was meant to mimic what a human would see navigating a real environment while wearing an AR headset that can receive visual communication from their robot teammate who is independently exploring the same environment. So all of the visualizations that we tested in this experiment were different forms of time bar. The first is called an overall task time bar, and it shows the time elapsed, time remaining, and the time cost of getting to an exit point. So as time moves on, the red portion gets bigger and the green portion gets smaller. The next was our summary time cost time bar, which shows elapsed and remaining time, as well as the potential time needed to evaluate all of the targets inside of a building. And the last is a target summary time bar, which shows time elapsed, remaining, the exit cost, and then also the potential time cost of evaluating a single target found by the robot. So we used this simulation to answer the research question, what is the effect of augmented reality visualizations on the situation awareness of participants who watched videos of our simulated task? So due to COVID-19, it wasn't an option for us to have participants do the experiment themselves. And so we filmed videos from the human perspective instead. And we ran a 2x2x2 between subjects experiment that evaluated our different time bar visualizations alone and in combination, and we measured situation awareness with survey questions. We hypothesized that the time bar visualizations would promote better situation awareness because they provide information about aspects of the task that are most relevant to time constraints and decision making. And actually, our results did not support our hypothesis that the time bars helped situation awareness. And in some cases, our results suggested that if we were to gather more data, it may be the case that certain time bar combinations actually harm situation awareness. However, situation awareness is something that takes mental effort to create. It's built and maintained on purpose by a user. And we thought that since our participants passively watched videos and did not have to make any decisions, it's probable that situation awareness was less necessary or perhaps unnecessary. I'm sorry, when did I become muted?
Sorry, someone came in, I hit admit, and then it popped off, and then I hit mute on you. My apologies.
We missed like 5 seconds of you talking.
Okay, so participants in our task watched videos passively, and so it's highly probable that they had no need to build and maintain situation awareness. So future research should make sure that tasks used in experiments guarantee the need for participants to build situation awareness, either by having them complete a simulated task themselves, or ideally by having them do real-time collaborative search with a robot and an AR headset. And despite our inconclusive results, we think that this experiment gives good insight into potential issues with passive tasks in user studies that measure situation awareness. And overall, situation awareness is still a really important consideration for augmented reality that supports human-robot teams. Thank you.
All right, thank you. Okay, next up we have paper number 4, Gregory Lamassier. Sorry if I butchered that.
Okay. Hello, everyone. My name is Gregory VAM-HRI, and I'm a master's student in the Human Robot Interaction Lab at the University of Massachusetts Lowell. And today I'll be presenting our paper, Semi-Autonomous Planning and Visualization in Virtual Reality. We had previously presented our interface at VAM-HRI 2020, and we had focused on providing different levels of control to a user in VR. We were concerned that if we did not provide controls that were commonly used in 2D interfaces, then a user would be required to take off their headset and use a supplementary interface. After internal testing, we found that our design was actually limiting controls to mimic those that were commonly found in 2D interfaces by providing similar menu options and requiring users to switch modes to access additional functionality. In the new iteration of our interface, we offer new control methods that take advantage of the strengths of virtual reality. When designing our interface, we took inspiration from the 2D interfaces used at the DARPA Robotics Challenge. The DARPA Robotics Challenge is a competition where teams competed to perform various tasks using humanoid robots. And additionally, we have expanded our interface to include human-in-the-loop planning, which has seen success in the DARPA Robotics Challenge. To enable planning in the virtual world, we proposed the concept of functional waypoints. Functional waypoints are different than traditional waypoints in that they not only provide a position and orientation information of a goal and a trajectory, but they also enable an operator to send commands that will alter the robot's state at this particular waypoint. This enables an operator to fluently create a complete and complex plan to complete a task. After an operator approves of the plan, they are free to monitor the robot or work on other tasks. On the left, you can see an example of our navigation functional waypoint, where an operator is able to adjust the height of the robot using a slider interface on the robot's back. And on the right, you can see an example of a manipulation functional waypoint, where an operator is able to adjust how open or closed the end effector should be at each waypoint. So first, we have our navigation functional waypoints. These navigation functional waypoints have a collision avoidance toggle at the top. When enabled, the user is unable to place a waypoint in a location that would collide with its environment. And as we had mentioned before, an operator is able to adjust the height of the robot using the slider interface in the back, which is necessary in order to get a better vantage point of the environment. An operator can create these waypoints in 3 methods. First, in the top left, an operator can use the point and click method to point a location in the world, which will create a navigation waypoint at that point. Additionally, they can grab onto an existing functional waypoint and press the trigger button, as seen in the top right, which will create a clone of the waypoint that they were holding. In the bottom left, you can see that an operator is able to use our virtual wristwatch panel to create a new navigation waypoint. And additionally, we have added other path visualization methods to our interface to show the operator the robot's planned path to a navigation waypoint, as can be seen in the bottom right corner. We've also added manipulation functional waypoints. These allow an operator to specify a trajectory for the robot to follow, as can be seen in the left-hand image. And as mentioned before, an operator can use the slider interface to indicate how opened or closed a robot's end effector should be at a particular waypoint. When executing the plan, the robot will first reach the functional waypoint, and then once it has reached this functional waypoint, it will then execute all state commands that were provided on this waypoint. On the right, you can see an operator is able to adjust the orientation to match that of an object that they have identified in the point cloud. To provide human-in-the-loop planning, we have also added several plan visualization methods to our interface. On the left, you can see the turquoise robot is depicting the robot's planned trajectory to the operator. If the operator is satisfied with this trajectory, they can then approve the plan, and then the real robot will execute the same exact trajectory. And on the right, you can see various statuses of our functional waypoints. Initially, these functional waypoints are blue in color. And then once our system has detected that a waypoint is likely to be out of reach from the robot, it will become orange to indicate this warning to the operator. And if the robot fails to plan to a particular waypoint, it will turn red to indicate this error to the operator. Here you can find videos of our navigation and manipulation planning interfaces used with the real robot system. I'll be happy to answer all questions during the breakout question and answer session. Thank you.
Great, thank you. Great talk. All right, next we have paper 5 with Martina Mera.
So all right. Hi, everybody. Thanks for organizing this great workshop and thanks for having us today. I'm presenting the Cobot Studio project. It's a project that my lab has been working on for the past 1.5 years with many partners from different disciplines such as robotics, game design, VR, and psychology. With the project, we want to contribute to a human-centered future of human-robot collaboration by exploring relations between robotic intention signals and trust on the part of the human collaborator. We conduct investigations on effects of interpretability and predictability of collaborative robots, cobots in short, in industrial work environments. As we are convinced that VR games have great potential for research because, tasks and experiences within the game feel really relevant to our participants, and because robot behavior can be kept constant, which is important for science, we created a VR cobot game in Unity last year, which feels like a game, but which serves us as a highly functional lab for controlled experimental research. So in the game, we send our players in a fictional rubber duck factory by means of an HTC Vive headset. The narrator explains the tasks. So far, we have implemented 3 mini games in which you have to pack or find rubber ducks together with virtual industrial robots whose intention signals we manipulate. To be successful in the game, it's important to understand the robot signals and react accordingly to them. I'll show you some short video excerpts from a user's perspective. So here we are in the tutorial room of our game. Players can move freely around and learn to interact with objects, either by a controller or by hand tracking. What I want to mention is that even though our game is fictional, our virtual robots are not simply animated characters, but digital twins of real robots controlled with the same software as their physical counterparts. Here we see an excerpt of minigame 1, in which players have to guess the target location of the mobile robot in the room, which is our performance measure for predictability. They can simply select a floor tile where they think the robot will stop. So here's another short clip from our minigame 2, in which players face a stationary robot and have to guess as quickly as possible which object the robot wants to grab next. Here too, we manipulate intention signals, for example, by having the robot orient itself completely in the direction of the target before starting to move. Yeah, we've also implemented event-triggered self-report scales for our subjective measures, which appear whenever they are relevant in the game and with which we can measure trust or perceived safety and so on. Okay, so this is an overview of our initial application that has the 3 mini-games implemented and how we use it for research. Before and after playing our VR game, participants fill out a questionnaire on personality factors or pre-experience. The VR game itself always starts with a tutorial, followed by 3 mini games in randomized order. Minigame 1 and 2 we have seen already. Minigame 3 is about packing duck boxes into a shipping box to get with a robot, and you have to understand when the robot wants you to take over. So we have randomizers implemented in the game. Each participant is assigned to 1 out of 4 different robot signal conditions in each of the mini games. We have objective performance measures for robot interpretability, as the number of correct items or the time used, and we also have subjective measures with our in situ surveys. To give you an example of our signal conditions, they might look like this. For example, in minigame 1, we have either pointing gestures by the robot to communicate where the robot wants to move to, or we have a light signal that indicates the direction and the remaining distance, for example. These are 2 examples out of 4. Okay, so what's the current status of the project? So far, a little more than 120 participants have taken part in our initial Cobot Studio game. The analyses are ongoing, but so far, to give you a glimpse, the data seem to indicate that, for example, in minigame 1, pointing gestures are much more effective than the light signals. So what's next? We want to expand our research questions and also the mini games. Our main goal for the upcoming year is to create more dynamic and more natural and also longer interaction sequences in our games. And we also plan to switch from pure VR to mixed reality. Our game environment is built in a very versatile and modular way, so we can replace the virtual Cobot representation with a physical Cobot, for example, and this is what we want to do. Thank you very much. I'm looking forward to the Q&A session.
All right, thank you. So let's see. We have a couple minutes before our next keynote talk. And yes, thank you everyone for the talks. One thing I want to point out though before we move on is that all of our papers are going to be on our website. I'm going to link it right now in our chat. Oops, hold on. Timer's going off. So if anyone wants to grab those papers to facilitate a discussion or want them later, they're all there. And with that, I'm going to pass off to Christine.
Hi, thanks, Michael. So I have the pleasure of introducing our next session. It's presented by our second keynote speaker of the day, Paromita Mitra. I first met Paromita during a NASA-sponsored event for college students where teams were challenged to design augmented reality heads-up displays for astronauts to use during spacewalks. And I personally credit that program with inspiring me to involve AR in my own research. So that's just a little side note. Paromita works at NASA Johnson Space Center in the Human Interface branch, and Avionics Systems Division as the principal investigator for the Joint Augmented Reality Visual Informatics System project. Her team builds the displays and controls for NASA's next generation lunar spacesuit, the XEMU. Her research encompasses graphical displays, optical systems, augmented reality, and developing a heads-up display helmet apparatus to aid in astronaut performance, cognitive workload, and user experience. She has held positions working as an engineer on F-35 engines, designing Earth science satellites, and analyzing human psychophysiology and cognitive behavior for software development. Paromita holds a master's and bachelor's degrees in aerospace engineering from Mississippi State University. Please join me in welcoming Paromita.
Hi, everyone. And hi, Christine. Thank you for that kind welcome. It's really good to see you again in person, and great job on this event. I got to sit in on the last few presentations and they were pretty awesome. So, yeah, thank you so much for having me. I'll go ahead and share my screen. I am not as well versed in Zoom because we use Teams and I'm using my personal laptop. So bear with me. Are you seeing my screen okay?
Yeah, we can see it.
Perfect. Awesome. So yeah, much like Christine mentioned, I will be speaking to you guys today about a few different elements of my job. I know that a lot of the presentations you guys have been sitting in on are research heavy, metric heavy. I wish I could dive into that with you all. We should have some things published by the end of this year that I'll be able to present at some conferences, and we're looking at a few of those, likely IEEE and maybe this one as well is really interesting. So I have a few hats that I wear at JSC at NASA Johnson Space Center. And so I'll give you a quick background of where I fit into the bigger organizational structure, give you an idea of what the type of work is that's going on in the world of EVA displays. So if you hear the word EVA often, if you're not a space nut, it just stands for extravehicular activity. It means spacewalk. When you leave the craft, you wear the suit. And that's when a lot of hard tasks happen that need a lot of aid. And so I'll get into some display work that we're doing, both from a project perspective, from a suit perspective, as well as from the Suits Design Challenge that Christine actually competed in that she just mentioned, and just kind of talk about how all of that fits together and how it's advancing some of the work that we do at Johnson. So I'll just jump right in. Just a quick background on myself. I do have a formal background in aerospace engineering. My thesis advisor, I actually know that she's very involved in this conference, Dr. Cindy Bethel. So she guided me through a lot of my study design in my master's program. I graduated in I want to say 2017 or so, and I've been at full time at NASA Johnson for about 3 years now. And so my job is, as one, I'm a PI for this project called Jarvis, Joint Augmented Reality Visual Informatics System. And that is essentially the project that's developing the displays for the suit. And there's a few other things I do on the suit. I'm technically the component owner. It's a separate project from where the funding from Jarvis comes from. But same hat. I also own the tool port on the suit. So that is an interesting engineering challenge because you're enabling lots of different types of tools to be able to interface with the suit one day. I also run the Suits Design Challenge, which is NASA's first Artemis specific lunar specific software design challenge focused around augmented reality. And then also, as of recent, I'm managing the Human Integrated Vehicles and Environments lab. And so that's another piece of my responsibility at work. So just to give you an understanding of the org structure, so I'm in the engineering directorate. There's all of these different groups that work within it. I'm specifically in the avionics systems division, and within that division, I'm in the human interface branch. So anything that the crew touches or interacts with, so whether that's photo, video, audio, using your 5 senses, the communication systems, what have you. And so a lot of that does focus around displays and display work. And so that's kind of where my contributions lie. The XEMU, or the Extravehicular Mobility Unit, is the larger suit system that I am a part of. But on that suit, there's a few new efforts. But let me give you an understanding of where the suit is going and what it's doing. So in 2023, there is a slated flight for this new spacesuit on the International Space Station to be flown. There's also a few flights for initial lunar and sustained lunar. So those are two different missions that NASA kind of defines as a way to get boots on the moon in 2024, as well as the sustained mission, similar to when we did Apollo, to have follow-on missions and the associated technology that goes with that. So there's three various subsystems that make up the suit. There's the pressure garment system, pretty straightforward what that is. It's the garment itself. It's what you see here, that this is called the hut, the hard upper torso. There's it encompasses the helmet, any of the bearings here. There's also the portable life support system, or XPLIS as we call it, and that is the backpack of the suit. So everything that has the life support system inside of it. But as of recent, about 5 or 6 years ago, there's a brand new baby subsystem, and that's the subsystem I'm a part of. It's called informatics. And so this is a way to get technology. So informatics subsystem, or XInfo as we're called, is our responsibility is to develop modular technology on the suit that's upgradable over time. A lot of what you see on the suit is a life critical system, which means when you have Crit 1 technology, it's really high fidelity, high redundancy. So you have to have highly reliable systems. But you know, there's a lot of commercially available technology as well that's useful to be able to upgrade and modify the suit over time. And so informatics exists now as a way to add, to give added capability for elevated autonomy as we go to future lunar missions and Martian surfaces. Within the XEMU, so this is a pictorial that pretty much describes all of the new upgrades to the suit. So for many of us, and before I ever really started working in these groups, I wasn't aware of, you know, really the history of suits in general. So spacesuits, we have the current oldest technology that's flying, the oldest spacecraft that is in flight right now is the EMU spacesuit. So that is the spacesuit that's used on the International Space Station. And then this would be a very different upgrade to it. There's so many different added capabilities. Namely, I mean, the structure of the suit is completely a different concept. Where the EMU suit is completely bubble pressurized, this has a hard upper torso with a hard pressurized torso, allows for better mobility in the hip area, in the joints, and the groin there. And then along with that, there's quite a lot of other added capability on the suit. Pertaining to XInfo, it's the displays and controls. There's HD video and lights. So actually just last week, we flew a new camera on the old suit on ISS. So if you haven't checked that out, I would highly recommend. It's called looking up the HECA, or the last EVA, the second to last EVA we just did. And so you get to see, you know, first time real HD video from the suit, which was really interesting in a first person view. But similarly, we're having a HD camera on the suit and lights, and then high speed data and comm. And so all of these things are ultimately the pieces that we need to enable this shift in autonomy as we go to more independent missions and get further and further away from planet Earth. So the informatics subsystem, like I mentioned, the primary mission statement is to enable autonomy, efficiency, and effectiveness. And so to do that, there's quite a few components of that subsystem, lights, camera, the processor, the tool port, the displays and controls, what have you. And so Jarvis really came about as a solution to an existing problem. With the Boots on the Moon 2024 schedule and this initial lunar schedule, there's been quite a huge schedule shift in getting a suit on the moon as soon as possible, which is exciting. However, there is a huge gap in the technology that needs to exist on the suit to enable displays and controls. So not only are we trying to understand, the human performance impacts, but we're also trying to, and we've been successful in delivering hardware and software that will ultimately be the AR display solution. And so the deliverables from this funding path is really to reduce the risk for the XCMU project to be able to, whenever they move these requirements for the displays and controls from this deferred status to an active status, that it will be a pretty easy path forward and minimize any redesign cost and schedule impacts. And so right now, NASA oftentimes works off of TRL, or technology readiness levels. And so there's a few really novel challenges that we're experiencing in the suit when we want to enable an AR display, and I'll get into some of those novel problems in our approach to them. One other thing to note: this is not funded by XCMU. This is actually a separate funding path through headquarters through the Early Career Initiative. So that's just a caveat I like to include so that we know that this is still needs to be a proven technology before it flies. So why do we need, what are the optics problems and the novel challenges we have in the suit? Traditionally, we have head-mounted displays and heads-up displays that we are very familiar with in the industry. So with HMDs, you have a smaller eye relief distance, your distance to, among many other constraints, the distance between your eye to the final image substrate, whether the image plane. And so with the HMD, you have a headlock device, and it's the eye relief distance is very tiny, a few millimeters. So think Google Glass, HoloLens, and then you have your heads-up displays in cockpits for jet and you have head-up displays for fighter pilot that fighter pilots typically use, or car displays. And so those are a larger eye relief distance. So the geometry and the fundamental basis of the technology is very vastly different from one another. Typically in a head-up display, you can use some sort of reflection device, and the optics can be much more simple, but things like the eye box and how far you can move your head to resolve that image is varied. And those are two vastly different optics problems. But in the suit, we have this medium eye relief distance at the helmet bubble. There's a few other requirements to not have anything mounted on the head, especially as a brand new technology within this life-critical environment. In 100% O2 environment inside of the suit, there's a lot of rationale to keep any hardware off of the head and keep it outside of the suit. As we all know, 100% O2 environment is rather flammable, and so having something to qualify within that suit would have to be a really tried and true device that we are prioritizing as higher than a low criticality system. And so with all of these challenges, we have this need for a novel optics solution. We did multiple market studies, and there isn't currently anything that gives you this medium eye relief distance. We're coining the term heads in display, or HID, or really anything that, any technology on the market that exists for that. And so we've been pursuing a few different paths, but beyond just this optics challenge, there's quite a few other things as well. So we have this novel optics challenge. getting to the moon is being on the moon is a very harsh environment. And so thinking about heavy ion qualification for hardware is a really big issue, and specifically in the world of displays and radiation tolerant GPUs. And so we have an effort that's looking at that. But from an operations and software perspective, there's other really big impacts. So operationally speaking, this is the first time that the EVA world will have a dynamic changing visual display in the loop. So today, the current operations for mission control to the EVA crew member is to have a live audio feed. Beyond that, there are instructions that are used on the cuff on a flip book that's taped to the cuff checklist, is what they call it. And that cuff checklist actually is just emergency protocol in case something goes wrong. And so from that perspective, we're really introducing this shift in the operator control scheme. And so understanding who has authority, who has responsibility is something that really has to become tangible, and everything down to the training products to how we provide rationale and quantify our system control architecture. That's a really big push for us this year, is understanding that control architecture. From a software perspective, we really need to understand, just everything down to the core flight software, or CFS, as NASA's many flight systems use. How do we incorporate all of the different display feature functions within that core flight software architecture and execute that on the UI? How do we make sure that we have a safety critical framework that can fly a reliable UI framework? So there's a lot of off-the-shelf UI frameworks that exist, like iData, GL Studio, that we've looked at, and we're really at this point going with a custom UI renderer, which has been a recent shift and an exciting decision for us. But there's a lot of work that's going on in each of these three big efforts: hardware, software, and operations. And that's really how we've structured the team. And then I'll also get into a little bit of the test and integration environments that we've enabled, and the extensive test and integration environments that need to exist to be able to test hardware that hasn't been complete yet. And so I'll show you how we're doing that as well. This next slide is explaining a little bit about our approach to external partners and what each of the partners are doing. So I mentioned earlier that we have to have a radiation tolerant GPU. So we're funding 2 PhD students at the SHREC Center. It's an NSF Center for Space High Performance and Resilient Computing Center is what it stands for. And so it's a conglomeration of schools, of universities that focus in radiation tolerant compute systems. We also have a partnership with MIT Nano. Excuse me, I've got a rogue mouse. We've got a partnership with two optics groups and photonics groups at Nano, which is a new nanotechnology research facility in Cambridge. And through that, they're actually developing 2 separate passive optics that are going to be extending the eye relief to that medium eye relief distance that I was mentioning. So very excited about that. I think we're closing the gap there on that TRL. And then from an industry, an academic so everyone's academia here, but from another academic perspective, and this is really where I feel like we're answering a lot of the unanswered questions of the display system, is through the NASA Suits Design Challenge. We also have a partnership through a Space Act agreement with Microsoft HoloLens, and we're looking into some partnerships with Unity as well as Magic Leap and some other AR companies. And so the NASA Suits Challenge is really a way to take all of the problems that we can't solve today because of our limitations on the architecture in the suit, and asking academia and students to really start to pursue that. as I've seen in some of your presentations, AR is a obvious choice to enable everything from human teaming control schemes to robot control to interacting with faraway assets on planet Earth. And so that suit's design challenge is really there to enable research and exploration for the purposes of EVA, which is when I entered the field in 2014. I think there was like one or two other AR focused papers based on EVA. And so I think this has been a really good effort as well. Okay, so this is a really busy eye chart, but I do want to show this because it kind of shows the team breakdown and where things touch what and all of the components. But let's start on the right side of this chart. So as I mentioned earlier, we've got hardware, software, and operations. I live here. Our systems engineers folks live all across the board. I also do much of the systems engineering work for the project. We all wear multiple hats, but this is just to kind of show the components of the Jarvis project and how we've broken things down and have had to think about this from an engineering perspective. So the ops team is really responsible for defining what the display will do and how it will do that. So we have flight controllers on the team, from EVA flight controllers from mission control. We've got PhDs in folks who've gotten their PhDs in operations and understanding how we work in an EVA system. And so they have really helped to take all of the 150 requirements or so that existed on the suit and boiled them down into these functional capabilities. So today, the Jarvis system can be a procedure manager. It can process photo and video and be an aid to camera and imagery systems, as well as read suit telemetry. There's a navigation piece that we want to explore, but it is out of scope because navigation is considered a CRIT 1 function at the agency. And so we have to have a CRIT 1 architecture, but informatics as a whole by nature is upgradable and modifiable. So how do we enable a nav display on our system? And then how do we use that? So as the agency as a whole is really looking at navigation and what that looks like for the moon. But that's definitely one of the features that are out of scope for right now for initial lunar, but is something that needs dedicated attention to. And so the suit's design challenge mission description this year is very focused around the navigation piece. And I'll get into suits later. I've got a whole few slides there. So all of these features are really informing the UI development. And the UI, they make up the UI in itself. And then the UI obviously has this core flight software piece that I mentioned earlier. That is the flight software that will fly. It's custom front end, back end, separate from what actually is shown on the hardware. We have a VR test bed that we've mocked up the suit helmet, the optics of the helmet bubble, the UI itself within a lunar environment so that we can change the lighting conditions, understand the various and change around UI design. So we have a UI UX designer dedicated to that UI development in VR. A lot of this is all informed by the ops group. So they run these 4 different test beds. One is just in the Hive lab doing shirt sleeve testing. Excuse me. I really need to get a new mouse. And so then another one is the NBL, the Neutral Buoyancy Lab at NASA. That's where they do the underwater testing for EVAs and to practice where crew train for EVAs. So we have a display in the NBL that we can do some voice recognition testing on. We have a rock yard, which is just this giant, exactly what it sounds like, yard full of rocks at JSC, and so that's also used as an analog for EVA operations. And then we have this VR testbed. That VR testbed is also now being used as an ops training product. So the EVA flight controllers can now use our assets from our Unreal assets, insert them into their training VR environment and use them as they wish. Another really big focus of this year is controls. So controlling the software and what it does is very important, but it is a big push in this fiscal year. And then the hardware team is working tirelessly to figure out what the switch and mounting embedded software needs to be for that front end control. And the operations team is really defining what the remote control from MCC would look like, what a switch control would look like, what a voice control scheme would look like, and what that hybrid option that we're probably going to take is going to look like. And so defining those control schemes and then developing test plans so that we could use those test plans to inform our design is really kind of where all that work comes together. Shrek, again, doing the GPU, CPU radiation mitigation work, MIT focusing on optics, and manufacturing those components. And then we've got the hardware team doing everything down to the projector, FPGA, PCB development, to the firmware development. Cable harnessing is a really big thing in this suit because of the reliability and the specific military grade harnesses we need to use, and then obviously running all of the tests and analysis that's needed to get to flight. So that's in a nutshell. I know that was super short, and I'm sure that you'll memorize all of that, but that in a nutshell, that's what the team is doing across the board and all of the different efforts that they're working on. And from a hardware overview perspective, this is a rendering of the suit that's publicly released, but I just wanted to point to some of the areas that we intend to have our hardware. So right now we're looking at switch controls for on-off switch in between the lights here. This is the camera on the suit. So just a caveat, all of this entire band belongs to the informatics subsystem. So a display with a projector would possibly mount right in between the camera and the helmet there. We'd have the image forming optics that would begin at the outlet of the DLP projector. And then we have two layers of one transparent substrate and one beam steering optics that Professor Bulovic and Professor Gu's groups are developing for the front end optics. And then here I have on the left that VR scene that I was telling you about. This is not at all our UI, but I wanted to show you kind of what the dark side, the shadowed areas of the moon looks like. We actually have a more higher fidelity light engine now that I haven't turned into a video just yet, but this is our VR scene. So you can see this is completely upgradable. This is completely changeable. You could change the color, font. It's really just like almost like Microsoft Paint. You can put whatever window you want in here and stream whatever that is. So it's got a lot of capability to do rapid prototyping. And this is a first look at the nanoparticle film that we're getting from MIT. And it's reading the projector and it's literally taped on. That's how tiny the film can be. But it's coated with various nanoparticles that I don't mean to be vague, but the nanoparticles themselves have a resonant frequency, and when they interact with specific wavelengths of light, the resonant frequencies actually match up, and that's how you're able to see and capture an image on almost a completely transparent screen there. Awesome. So then just getting into requirements. So there's quite a few requirements on the helmet, on the suit for the helmet, but there's it really boils down to some of these functions. I mentioned earlier that there's a really big question about nav, and so I have it highlighted because in the next section I want to kind of get into how we're focusing on navigation and some of the outcomes we're hoping to see from suits. So what is NASA Suits? I've mentioned it a few times. It stands for Spacesuit User Interface Technologies for Students. And so it is NASA's first software design challenge, and it's really focused on developing AR displays. NASA gives, from our side, we define a mission description. We provide a telemetry stream and possibly task instructions if there's a task associated. This year, we're providing coordinates and locations for the students at various points so that they can then input those into their UI designs. Many students use Unity. I think some other students use Unreal. Yeah, so that this essentially the students are developing a display within their AR devices, and then when it's not coronavirus, they come on site, the top 10 teams, and then we have subject matter experts who run through the entire display and do an actual EVA. And those subject matter experts span everyone from display engineers to the EVA flight controllers to crew members. And it's really valuable because that's the people that are actually developing and working on these systems, seeing kind of the pie in the sky ideas. Key members and stakeholders. Chris Hansen is the EVA office manager, so he's in charge of like all things EVA at Johnson, which is really neat. But then we also, this is kind of a cross-organization effort through the Office of STEM Engagement and Microsoft, as well as the EVA office. This is really unique because typically these types of challenges are very OSTEM focused, but this is the first time that a challenge is being paid for through an engineering organization. And so I'm the technical lead, so is Chris Gertie. He's also the informatics subsystem lead. And then this year usually the interns, I have a few interns who will work the Suits design challenge, as well as some other aspects of the informatics work. And this year, Liam Smago is our intern for spring and summer. And then this is our awesome team of OSTEM folks who help do the coordination of the event and run the challenge. And anyone, any university team can qualify for this challenge. And I'll show you the timeline if in case y'all are interested in joining next year. So this is just a quick eye chart to kind of show you what's going on right now. For 2021, we've selected 20 teams. Usually it's just 10 teams, but because of COVID and because everyone's in telework, we took the advantage and the opportunity to be able to select more teams. And then next week, we actually have a design review where it will then boil down to the next 10 teams. And then those 10 teams will send their HoloLenses or Magic Leaps or Google Glass, whatever, to JSC, and we'll test them. Some upcoming events, again, the design review, and then our test week is April 19th through the 23rd.
And Paromita, if you want to wrap up in the next couple of minutes so we can have a little bit of time for Q&A, that would be awesome. This is really interesting. Sorry to cut you off.
No, I know it's so much information. I never know how to get through it in time. So this is just a quick eye chart of the timelines and the milestones. And I have 3 more slides and I'm done. So the next one is just giving you an overview of what Suits has done in the past. So first 2 years was really focused on an International Space Station task. This was our pilot year. Again, another more high fidelity International Space Station task. So I think someone's mic is unmuted. Okay. And then in 2019, we did an actual solar it was the roll ring module for the solar bearings, solar panels. And so that was the kind of the main task that was focused around. 2020 was coronavirus happened, but the real intention was to start the first lunar specific task. And so the initial intent was to have this SEV rover is what it's called, and do a tire change on it. But going into 2021, we have a very nav focused challenge. So this year we gave the students 3 navigation goals, and they'll have just this week, we're actually dropping the coordinate points. So hopefully the students can quickly turn those around before the end of the time they have to come on site. And so that's kind of the Easter egg there. There's a science sampling interaction, and we define some high level goals that we wish for the students to complete, as well as the suit telemetry stream functions. And then I wanted to leave you with this slide specifically because this community has a lot of significant research that's being done. And these are some of the bigger R&D questions we have that need exploration for the purposes of EVA. And feel free to screenshot it, feel free to replay this recording at a later time. But really, there's a few questions, and the ones in yellow are pertinent. But from a navigational perspective, how does something like an AR device aid in any sort of path planning or navigation solution? What does that look like with very minimal resources and power on the lunar surface? Another one that I'd like to highlight is specifically from a MCC perspective, what is that control scheme and what is the authority and responsibility delineation as you have 2 EV crew members, an IV crew member, MCC, and what have you. So these are some really interesting and exciting questions, but they need tons of work done on them to be able to answer and focused research and dedicated research. So with that, I will stop my presentation. Thank you so much for listening and take any questions.
Thank you so much, Paromita. That was amazing.
Yeah,
really
absolutely.
cool talk. Learned a lot from that. I know that we're a little shorter on the questions, so if anyone wants, they can raise their hand or ask their questions in chat. Hunter, go ahead.
Hi, Paromita. My question was looking at control, using the heads-up display for control of other robots. Is that something that you've talked at all about?
So that's a great question. We've actually seen some really neat demonstrations through the Suits Design Challenge of a robotic control system. I believe it was Kent State from last year that showcase, and that was the first time we really had a robotic control, like a teaming type of solution, which was super interesting. And so that is the first time we've seen anything like that. But as soon as, during the exit pitch for Suits, there was EVA office, Chris Hansen was there, crew members were there, and that was something that really caught everyone's attention. It's not something that's currently in the architecture of Artemis and the lunar missions. So it's not a requirement for us to work towards, but there is a huge requirement for connectivity of things. So for instance, a lot of what is the wireless access point? And so those architectures and things are being defined right now. And so ultimately, hopefully, understanding what that network is going to enable things like robotic control via a display.
Great, thanks.
Yeah.
Does anyone else have any other questions? You can raise your hand or post your question in the chat. If not, I'll ask a question. I was curious, can you talk a little more about that camera that you said was on the suit? I was just kind of curious, because you mentioned that. I was curious, if there's anything being used, how that information is being processed. Because you also mentioned the connection maybe between working with Magic Leap or HoloLens. So I know these headsets, they normally make they try to create geometric representations of their environment. I was wondering if you guys are doing anything like mapping. Or is that too heavy processing? And I was just kind of curious about how the sensors are being used.
That's a really great question. Right now, the the only processing that happens of the images is just it's all sent to ground, and ground uses those visuals. Now, with the introduction of a helmet display, we will have a viewfinder where the crew can see the view of their camera, which is the first time that something like that would ever happen. And so just this month, so this is our sprint right now, we're in the middle of our sprint for our camera and imagery function. So we're trying to understand what are some of the low-level overlays that we can do on top of this viewfinder to benefit the system. And so that's one angle. There's also some interesting work that was done out of Draper Labs in Cambridge on using point space waypoints defined by just a camera image, and arbitrary waypoints that are placed on that image itself, not something that's actually in the environment. So it was in a nav system essentially using camera tracking as a way to set waypoints, which was really fascinating. And so I know that the EVA office has been in talks with Draper regarding that work. But beyond that, right now, no, but it is very big interest and people are looking into it.
Great, thank you.
Yeah.
Well, that's all the times that we had scheduled for questions. So now we're ready for our 10-minute social talk / breaks. So we'll be getting back together in 10 minutes. And so feel free to take some time and ask questions on the Slack about the keynotes or any of the presentations that have happened up to this point. And yeah, see everyone in 10 minutes.
Yeah, thanks.
Thank you so much, Paromita, for joining us.
Thank you so much.
Hopefully this should be the right screen. Okay. So my name is Christian Barentine. I am here presenting our work on teleoperation in VR with manipulation assist. So as you know, teleoperation is when a human assists with operating a robot. And we have found that VR has had enormous advantages for the effectiveness of that operation. So what motivated our study or our system development is that while teleoperating a robot can be useful, we've had issues with disconnects between operating a robot with a 2D system like a screen, and like how that disconnects the operator from the environment that the robot is working in. All right, so we've implemented VR teleoperation to deal with that. However, our VR teleoperation has also been sort of slow, right? For simple cup stacking tasks, direct control has led to like task completion times on the order of like 3 or 4 minutes just for stacking 3 or 4 cups. So to deal with that, we created a manipulation assist algorithm to attempt to let the robot handle the fine detail, fine-grained controls of like actually manipulating objects, and let humans handle the overall, high-level goals of where the robot should go and what it should do next. So our research in this in particular is focused on 2 types of sort of control paradigms, right? One paradigm is permission-based, where, let's say you're trying to pick up an object, you select the object, and then the control system will populate with a list of, these are the different things I can assist you with related to this object. You select one, and then the robot performs the assist and then returns control back to you. The other is exception-based control. So you select an object, the robot begins its assist based on what it believes the like assist that you want to do is, and if it is the incorrect one, then you have to press a button or otherwise interrupt the robot's actions. So the manipulation assist algorithm is actually pretty straightforward. It looks up the objects in a database. We have a list of different assists that can be performed for that object. Again, with permission, it gives you a list of all the ones that it can do. With exception, it just picks essentially the first one off that list. It then performs the assist by going through a series of waypoint moves and state changes defined in the assist, and then once it's done, it returns control back to you. This is made possible in part via a context manager, which keeps track of things like what object the robot is holding, or does it have a gripper free to pick up a specific object. And then, of course, it wouldn't be that useful if it didn't know where the objects were in real space. And since this wasn't what we were particularly interested in studying, we tried to use sort of an off-the-shelf Aryuko tag recognition software so that when a camera detects an object with a tag on it, we could render that in the VR headset. I should mention that this work is still very much a work in progress, so we're hoping to get some good feedback on that. So the experiment we were planning to do to sort of test the efficacy between assist by permission and assist by exception were a pair of object manipulation tasks. The first one is clutter pickup. So you can see on the left, we've got just a picture of several different colored cubes. The goal being, we want the participant to pick up all of the blue colored cubes, for instance. We think that would be an interesting challenge for that sort of manipulation assist. And the second task is to do sort of a multi-stage assist where first pick up a lid, then put the lid onto a pitcher, for example.
That's 5 minutes, Christian. So if you can just wrap up, please.
That's perfect, because that's actually it. So I'll be happy to answer any questions you have. And again, if you have any advice, feedback, please let me know.
All right. Great talk. Thank you.
You're able to see my screen, right?
Yes, we can see it.
Great. Thank you very much. My name is Andrew Watson, and I'm at the Cooperative Robotics Systems Lab at Arizona State. Today, I'll be presenting our work about virtual shadow rendering for maintaining situation awareness in proximal human-robot teaming. So humans have a limited field of view. So usually when we have a human-robot teaming, we are not able to keep an eye on the robot at all times. Imagine working in a workshop where you have to work collaboratively with a robot, but you need to focus on your own work while still collaborating with the robot. There's usually the need to keep an eye on the robot so that you don't waste your time looking at the robot all the time. Also, for safety reasons, you need to keep an eye on the robot. AR has actually come in to help us a lot because it's able to render or project holograms that are actually not part of our world to help us with such a cost. However, projecting things with AR actually causes a lot of distraction into the environment. It makes it complicated. So we propose a solution of using a phenomenon that's already known by humans. We've been living with it for a long time, which is shadows. We believe that projecting shadows will put extra information that are just necessary for the right course. So imagine, I'm going to show you a video here. This is a live video recorded with HoloLens of my project implementation. You can see the shadow being casted, and you can see robot at my back actually, and this is what I see up front, and the robot is actually at my back and it's being casted on the trash can right in front of me. So this is the implementation of our proposed solution, and so far it works very well. To get this thing to work, we used a lot of resources. We use the HoloLens, we use ROS, we use the URDF of the robots that we need, and we use Unity. So HoloLens already has a model of every environment that has been for anchoring purposes. It scans the environment, So what we did is that we made use of that, and we did a transparent model of that model that the HoloLens creates. We did this, and we actually, if you see the images, you can see I have a trash can here, and in the actual image, I have a trash can on the left. So there's a transparent cutout model of that, and you can see my shadow, and I was using the Jackal robot here. So what we do is that I do a cutout of the model, and then I put a directional light in our HoloLens in such a way that the robot shadow is always in front of the human being. Wherever you were, even if you turn left, it's always in front of you. Then what we do is that we superimpose this cutout model as a hologram onto the environment so that all the objects in the cutout model actually matches exactly with the things in our real world. This environment you see is pretty much the one that I showed you in the earlier picture. We did a study, and we made people test it with other methods that other baseline methods like map and arrow, where an arrow will be pointing onto the direction of our robot, or a map will show where the robot is. And we got some pretty interesting results back. As shown in our graph here, you can see that the gray one is our shadow method, and it's performing better than the map and the arrow in position when users were asked to actually indicate position just based on arrow, shadow, or map, orientation, and movement. We can see from our p-values here too that our data was significantly different. And to measure subjective tests, to measure the cognitive load, workload on people, we did a NASA TLX, and we can see from my graph here that my method actually did better than the baseline methods that we compared them with. We still had a lot of data to be taken, but it works better than all the others combined. So in conclusion, we addressed the problem of maintaining situational awareness in proximal human-robot learning. We applied AI technology to augment the existing objects to minimize distraction. And our method was effective and introduced less distraction. Actually, other studies that we did shows that it helped people to focus more. Any question, you can email me, or any contribution, anything that you think I should take care of, you can email me at my email. Thank you very much, and that'll be the end of my presentation.
All right, great, thank you. That's super interesting.
Awesome, okay. Again, sorry for all the issues, but good afternoon. My name is Chinmay, and I'm a part of Charisma Lab at Oregon State University. Today, I'll be presenting our paper titled Exploring Behavioral Anthropomorphism with Robots in Virtual Reality. So VR offers an instrumental environment in which robots and people can virtually interact. Our work attempts to intersect social robotics and VR, eliciting participant storytelling and behavioral anthropomorphism, revolving around the simplest possible anthropomorphizable robot, a robot that approaches and then bumps into you. Our inspiration for this study setup stemmed from two different influential works in HR and VR. On the left, you see the Robot Management System, or RMS, by Torres et al. This framework helps bring robotic experiments to the web. The RMS provides a customizable browser-based interface for robot control, integrated support for testing of multiple study conditions, and support for both simulated and physical environments. On the right, you see a picture from the paper by Simeon et al. This is a study that investigated users' level of engagement based on a physical proxy and a virtual object, and how the variations between the two affected engagement. One of their major findings was that shape matters for like an object to be believable, and also that there can be a certain degree of flexibility, which can be like a degree of suspension of disbelief, as long as the functional level of the object, both the physical and virtual, is maintained. The paper also proposed or explored this concept of substitutional reality, where every physical object in the user's surrounding is paired with a certain degree of discrepancy to a visual counterpart or a virtual counterpart. The authors presented a model of potential substitutions and validated it in two studies. So trying to bring these two together into our user study for HRI, we implemented a VR system. Specifically, our requirements for this were a physical robot and then like a virtual manifestation of the physical robot. This was tracked, the virtual robot tracked the physical robot using a VR tracker. There were mechanical toppers for the physical robot so that it could assume the shape of the virtual robot, be it a cylinder or a cube. And then before every user or for every participant, there was some degree of calibration. What this essentially gave us was that the participant observed a robot while they were immersed in VR. They could see both appearance and motion in virtual reality. This allowed us to easily vary that virtual appearance, enabling like testing or prototyping various visual variants of the same physical robot. This helped us save on robot build time, helped avoid hardware issues to a certain extent. There's always issues. And so basically going through our research manipulations, we had, when the participant walked into the room, there was an introduction where they were introduced to the VR system, told the protocol. They would then go through 12 different trials. In each trial, there was one material from these 12 trials that 12 materials that you see. The robot would take one of two paths, either a direct or indirect path, and it would also assume one of two shapes, either a cylinder or a cube. Between each trial, so there were 12 trials, and after each trial, the participant would be asked some survey questions along the lines of, was the robot friendly? Was it aggressive? Did you feel safe? Did you feel scared? Did you like the robot? Did you think the robot liked you? And this was for every trial. After all these 12 trials, there was an exit interview to delve further into people's perceptions of the robots and also like the system in general. Some of our interesting insights lied in this field or this area like of behavioral anthropomorphism. Recent developments in social robotics have shown that even simple robots with simple forms can be perceived as having human characteristics. For us, in our study, we saw that participants tended to form somewhat like associations and mental models about the robot. Some of these mental models included pets, dogs, and children. These mental models were along three different manipulations in the experiment. For example, for motion, these were some of the quotes that came up. One of the really interesting ones is the second one, where the participant went, this one doesn't give a beep. It is not aggressive per se, it's friendly-ish, but comes off as confused or a little bit drunk. The robot's meandering somewhere, like it's on its phone. It wasn't expecting to run into me. So there are all these kinds of different anthropomorphizations of the robot because of the immersiveness of virtual reality. Some of the other ones that revolved around collision are shown here. One that's interesting again is this like association to that drunk girl that the participant latched onto for the whole experiment. And then also for like the apparent materiality, that led to a lot of different associations too. Here's a quick video which shows how the immersiveness of this experience led to a propensity for physicality or play.
Okay, and just to say that was 5 minutes, so if you just want to wrap up after your video, but go ahead.
So for example, here you see the participant jump over the robot. They're obviously seeing a virtual robot. And then they also end up kicking the robot, kind of interacting with it. Some of our key takeaways here, and I'll quickly wrap up with this slide, are that VR can enable this rapid, flexible, low-cost explorations of character attributions for social robots. For example, for us, this the whole virtual setup literally costs $0 other than the hardware involved, because of the open sourceness of Unity. We also saw that color theory did not necessarily predict people's attributions, and we also saw that some materials, especially soft textured materials, weren't communicated properly to users because of like VR rendering, and so that might be something to explore later. Yeah, I'll just end here.
All right, great. Thank you for the talk. Next, we have Bryce Akita, if you'd like to share your screen. Yeah, we can.
All right, great. Hi, my name is Bryce Ikeda, and I'm part of Iron Lab at the University of Colorado Boulder. And today I'll be presenting our research on an augmented reality debugging tool for robotics programmers. Programming robots is hard, along with syntax, compile time, or runtime errors that make regular programming difficult. By adding a robot into the mix, we must also debug problems caused by variable environmental factors and irregular sensor reliability. Furthermore, while programming a robot, typical debugging techniques may not be the best choice. Why is that? Well, reading output print statements or log files can be confusing when reading complex data types as raw text. We aim to figure out how augmented reality can help improve this debugging process. Here are some examples of prior work revolved around AR displays to help roboticists. In the picture on the left, visualizations are overlaid on a 2D display using a top-down view of a swarm robotics application. In the middle, Colette and McDonald developed an AR debugging system that was also viewed on a TV screen. In the third picture, we see a tablet being used to display the robot motion intent to the user. The problem with the first two systems is that a TV screen can restrict the user's point of view to only the camera's point of view, and as well, they lack the stereoscopic view. Furthermore, by using a 2D screen, even a tablet, the user is forced to shift perspectives between the real world and the screen. This can both confuse the user and increase their mental load. Our solution is using a head-mounted display to provide an intuitive visual view of the inner state of the robot through in-situ visualizations. Additionally, Colette and McDonald identified 4 data types used by roboticists: geometric, vector, scalar, and abstract. Geometric data can be displayed in our system by directly viewing the data in the environment as their definition states. For example, in the picture in the top left, the estimated position of the turtlebot from the SLAM algorithm can be visualized as the turtlebot silhouette. For vector data, an example of this would be the pose and orientation of the robot's coordinate system placed in the user's environment. Examples of scalar data are distance measurements and rangefinder scans. By visualizing sensor data such as the laser rangefinder, this provides immediate validation of correct hardware performance. This can reduce the time to debug errors in a robot for a user because they can quickly identify which sensors may be working and which maybe not. For abstract data, we allow the user to customize these settings to display data of their choice. In the picture on the left, the top plate of the robot can be turned blue, green, or red. In the picture on the right, textual information is displayed. This can be used to show what the user wants to help them further understand their system. Our experimental design will consist of 2 stages. 1, an informal pilot study to gain feedback on the current state of our system, and 2, a larger ethnographic study to gain insight as to the effects of our system on a user's debugging practice. For both these stages, we will have the user program 2 tasks. 1, an object detection task, as seen in the top video, and 2, an object finder task, an example shown in the bottom video. We chose these 2 tasks because they are commonly performed by roboticists working with a mobile robot. To gain qualitative data, we will have each programmer perform a think out loud process during the 2 tasks to gain real-time insight into their debugging practice. We will then have them answer a survey based on the system usability scale. And lastly, we will conduct a post-interview to further analyze the effects of different visualizations on the programmer's debugging practice. For future work, we hope to expand this system to more complex scenarios. This could include detecting multiple objects in an environment, using different types of robots, such as those with end effectors, or expanding this to multi-robot systems. We also hope to do more studies to quantify the effects of our system on programmers. For example, understanding the actual effect on time, steps, or effort that it takes to program the robot. We welcome any feedback on how best to approach this idea. We look forward to continuing this work. Thank you for watching, and I'd be happy to answer any questions via Slack or email. Thank you.
Great. Thank you, Bryce. Great talk. And all right, so that brings us to our 10th and final paper. Padraig, if you'd like to go ahead.
Screen. Okay, and everyone sees that my screen all right?
I'm not seeing your screen.
Oh.
I can still hear you though.
Shoot, important to actually share. Okay, there we
That
go.
looks like it's loading. Yep, we can see it.
Oops. Okay, so my name is Padraig Higgins, and I'll be presenting our work towards making virtual human-robot interaction a reality. Okay, so kind of the goal of this work was just to be able to build a simulator where we could have like a fully embodied human and robot kind of interacting in a simulated environment. So the work we present here is kind of our simulator. They call it River, robot interaction in VR. And we're hoping that the use of kind of virtual reality and kind of realistic human avatars and kind of realistic environments will be able to kind of lower some of the sim-to-real gap, and then hopefully making it so that anything we learn in simulation, we don't have to kind of spend as much time kind of fine-tuning it in the real world. So kind of our work kind of had two main motivations. I think the first one was a lot of our work is in language grounding. So we need large amounts of information for kind of training. And ideally, this would be a kind of interactions in different settings, different objects, different tasks, and with as wide a variety of language as possible. And then kind of the second one was just kind of more broadly just improve accessibility to HRI research. And like robots are very expensive, and that's a big barrier to entry. And the second one was kind of we're hoping that being able to use a VR headset with a gaming laptop, we'd actually be able to get off campus and go to participants as opposed to expecting them to kind of come to us, and then hopefully kind of lowering bias in any kind of models that we learn. And just a bit about the simulator. Like everyone else, we're kind of using Unity to do all of kind of our rendering, and we're just breaking it down into two components. There's the client side, which is run on like a user's local machine, and that is just responsible for capturing all the user inputs, and it's responsible for all the physics simulation. And then we kind of offload all the rendering of any sensor data to a remote Unity kind of a client that is running on a server alongside ROS. And then just ROS is responsible for kind of processing all the sensor input and doing all the robot control. And then kind of everything is kind of stitched together with ROS Sharp. Okay, so this is kind of our first experiment we're planning on using this system for, and we're planning to do a kind of language grounding. It's just over raw speech as opposed to kind of more traditional methods which use kind of either transcribed or written text. So kind of we're breaking it down into like 3 phases. In the first one, we're going to have the robot, or in simulation, we're going to have the robot kind of asking users for descriptions of kind of food objects in like a kitchen setting. So I think you can see an example off to the right. And the robot would just kind of be able to ask some follow-up questions just to kind of gather a bit more information. And then kind of we'll move into a test phase where kind of we'll have the user instructing the robot to pack a lunch. So the user will kind of describe various objects in the setting, and the robot should identify them and pick them up and kind of put it into a little basket. And then finally, kind of the transfer phase, where we plan to kind of take the model that we learned in simulation and kind of transfer it out onto a real robot, and just compare see where the sim-to-real gap for where our kind of system is. And just kind of the future work is kind of transferring everything into the real world once COVID dies down. And we're also kind of there's interest in providing a kind of user interface to allow people to more easily modify scenes and import new robots into Unity. And then just kind of extra features that support interactive dialogue, kind of multiple humans, robots, and one of the other things we're interested in doing is there are noise models for depth sensors that we hope to integrate into our kind of that sensor pipeline so we can more accurately match the real world, and then just add ideally add more simulated sensor types, so we're thinking LiDAR or thermal. Okay, and I think that wraps it up for my presentation, and be happy to answer any questions in the breakouts.
Thanks. I think that's everyone, right? Just confirming it's everyone. All right, so that's the last lightning talk. What we have slotted next is actually breakout sessions. So I'm going to be making 3 breakout rooms. And if you're on the newest version of Slack, you will be able to just grab your own breakout room. How these are set up is, Eric talked about way at the beginning, we have different subdivisions of kind of the papers and the conference kind of topics. Here's what they are. I'll put them in chat and also show you where is the program I just had up. So here is the program. So if you're kind of in a mixed reality AR world, you're going to want to go to room 1. Room 2 is more general virtual reality. And then the third one is very specific in virtual reality for teleoperation. So you should be able to assign yourself into a room, and we'll do that for the next 35 minutes. Also, you can direct questions into the Slack, as well as, am I missing anything? Any other organizers?
I think that's it.
All right, so all the rooms should be open, and feel free to join whichever ones you want. And if anyone's having issues going to different rooms, just ping me via the Zoom chat, because I can just manually assign you as well. Ooh, thank you, Christine. And then, oh, I will stop the recording for this.